Good afternoon. Welcome to our second Anlinger lecture in energy and environment. I'm very pleased to introduce to you our speaker today, who is Professor Arunal Majumdar, who's the Almy and Agnes Maynard Chair Professor in Berkeley's College of Engineering. He's also a Professor of Mechanical Engineering and Professor of Material Science at Berkeley, and he directs the Environmental Energy Technologies Division at LBL, or Berkeley National Lab. Arun is an internationally renowned authority on the topics of nanoscale diagnostics, nanoscale energy conversion and transport, optomechanical devices, and the broad topic of bioengineering at the nanoscale. He got his DS degree from IIT Bombay, and then did his PhD work with Chen Tien at Berkeley. You know that Professor Tien was a distinguished Princeton alumnus. He started his academic career at Arizona State, moved to UC Santa Barbara, and in 1996 moved to Berkeley, where he's had a really stellar career. One of the many things that distinguish Arun's accomplishment is that he also has a very impressive record of professional service. I'll just mention some of the highlights in addition to his scholarly work. He served as chair of the Berkeley Nanosciences and Nanoengineering Institute. He was also a member of the Nanotechnology Technical Advisory Group to the President's Council of Advisors on Science and Technology. Served as the Council of Material Science and Engineering at the Department of Energy, and is a member of the Advisory Committee of the National Science Foundation's Engineering Director. He also serves on a number of editorial boards, including Nanoletters, International Journal of Heat and Mass Transfer, and he's received, of course, a large number of awards for his scholarship and research, including the Institute's Silver Medal at IIT, NSF Young Investigator Award, ASME Melbourne Medal, the Larson Memorial Award of the ASME, Distinguished Alumni Award of IIT Bombay in 2002, the ASME Heat Transfer Memorial Award 2006. He is a fellow of ASME and the American Association for the Advancement of Science, and was elected to the National Academy of Engineering in 2005. And he's going to talk to us today about using science to innovate efficient energy utilization. Pleasure to have you here.
I've got two mics out here. Well, thank you very much for the kind introduction. And it's an honor to be here. I was here last year, about a year ago, and it's always a little scary to come back within a year and ask, what's new? But this talk is going to be a little different from the last one. And what I thought I would do, given the occasion, is to give a first a broader overview of what I think and about the major issues in energy and the environment, and then focus and go deep into a topic that I work on. And as a result, I hope to keep it short, but it might be a little longish. So I'm just warning you. It's obviously a,
Obama only took 20 minutes.
It's obviously a very historic moment today, and there's a transition going on, and I think this is a transition in many ways. And energy and environment, as I think many of us think, is going to be at the forefront. The ideas that I'm going to present are not just mine. They have been influenced by many, among them my students and also my peers and my mentors, both in LBL and Berkeley and other places. So I'll just try to give first a broad overview. Initially, I'm going to just give you some facts. This is an audience that knows some of these areas very well, so I'll try to go over them quickly. So I'll come back to this picture later on, but give a context for that as well. So we know some of the, I think some of this is getting cut off out here, but here is a graph from a paper about 10 years ago about the carbon emission rate which is going up linearly. Today, it's about, 8 or 9 gigatons of carbon per year. And this is the totally primary power. And the fact that this is going up linearly is essentially a reflection of the gap between the demand increase and the fact that the renewables or non-carbon sources cannot keep up. That's the gap that we are facing. And of course, if this is increasing linearly, the CO2 accumulation in the atmosphere is sort of going non-linear. It's accelerating. And we might be business as usual. We might be at the double the pre-industrial level in about 50 or less than 50 years. And the big task for our generation or several generations is to how to turn the ship around. This is, it's not going to be easy. In the words of my now former boss, Steve Chu, this is, we are on the Titanic. And a lot of people thought there was no iceberg. But now people have started believing that there is an iceberg. And it takes 2 miles to turn the ship around. And the iceberg is 1.5 miles away. And some people are still shuffling the deck chairs. Hopefully, today and in the future, that will change. But that is a big ship. There's a huge inertia. And there's not one magic bullet. There are multiple things that have to be done. The question is, where are the priorities? The other thing that is, of course, I'll come back to this later on as well. If you look at where the global, I'm presenting a global picture first, and I'll get into the details. This is a huge mismatch. Here's Middle East, the oil supplies, and here are the coal reserves. The 4 biggest reserves of coal are in the United States, Russia, China, and India. And the 2 fastest growing economies are China and India. So there is, if push comes to shove, people are going to use coal. They are already using coal. And that business as usual is not a good scene. So given all this, one has to ask the question, business as usual is not going to work. So what are the things that will create inflections in the way we do things, in the inflections in the trends? And there's obviously a lot of things that have to be done. I just want to present this picture as well. Here is the carbon emission of selected countries, CO2 per capita, and is GDP per capita out here. United States over here. Australia is actually more than United States right now. Of course, per capita, China and India is over here. And of course, what the big challenge is how to bring United States down in its per capita CO2 emissions. But in addition to that, there's a further challenge of how, the question is, will China and India go that way, or will they go that way? And that is a big challenge in itself. And if this is business as usual, we are in for trouble. And so here is an opportunity in many ways for the United States and the rest of the world and India and China to work together to provide the technologies that would enable both these to happen. And the question is, what are those technologies? What are those policies? So clearly, it is a question of how do we, it's not just science and technology, and it's not just policies or markets of finance, etc. It's a combination. You cannot take anything in isolation. And the challenge is really how do we aggressively strategize in a way that coordinates, integrates, aligns, leverages, cooperates, all these in a way that reduces the carbon emissions, provides energy security, and affects climate change in a beneficial way. So that's what the thing is. And I'm not going to talk about, of course, Princeton has a lot of know-how in all of these. I'm going to focus on this. Because this alone cannot, but this in combination will. But this is an essential. The science and technology is an essential feature. What are the game-changing technologies which can really create inflections in the way, in our trends, in the CO2 emission rates? That's really the challenge. So I'm going to touch upon a few, and I'll basically reflect on my Berkeley experience of what we are trying to do. And that's the only experience I have. And then and that, of course, will address some of the bigger issues that I just presented. I start with this spaghetti chart. It's a way to start. This is the primary energy for the United States. Let's just talk about the United States now. These numbers are in quads, or quadrillion BTU. Or one quad is about approximately 1,000 joules. So the primary energy supply of the United States is about 100 quads. So these numbers are, you can think of them as percentages. You have your petroleum, natural gas, coal, nuclear, solar, wind, etc. This is the demand side out here. Where does the energy, where is it used? And in between, of course, is generation and transmission distribution. This is where the grid and everything lies. And one of the things that comes up is that we know all these are supplies, but the numbers are striking. And the numbers are, okay, so petroleum is 40. These are the domestic and imports, etc. Coal is 22 quads. Solar, this is a couple of years old. Solar is 0.006. So if you really want to scale up to be 6 quads, 1,000 times more, this industry has to grow at 35% growth rate for the next 25 years, so continue consecutively. That is a humongous task for any industry. And the question is business as usual, is that the way to go? Or should we be trying simultaneously something new? On the demand side, of course, you have the buildings as where the energy goes. And as I'll show, they're some of the leakiest energy hogs. Industrial, which is mostly paper, steel, cement. Cement is a big CO2 emitter in addition to using heat. And transportation. And in between is the distribution of electricity out here. I'll come back to this part later on. If 100 quads is used out here, 55 quads is lost as waste heat. And that is striking. And part of it has to be lost because of second law of thermodynamics, but not all 55. And there's still, second law does not limit you to lose this and not gain anything because the temperature at which it is lost is higher than ambient. So there's still juice out there. So now I'm going to come back to that, which is where my scientific work goes into. But nevertheless, let me just, this is the picture. Where do we start? Clearly, we have to amplify this. We have to decarbonize that. And we have to reduce this. And we have to transport and store some of the energy somewhere. Well, that's easier said than done. That's a huge task. And so it is not a single magic bullet out here or out there, but simultaneously doing all of that. And I think this is, we are probably and hopefully entering sort of a period of the next 10 to 20 or 30 years where we will see innovations, or we'll hope to create innovations, which is analogous to the invention of the transistor, the laser, the VLSI circuits, and internet, whatever happened in IT, all happening simultaneously. If you do not do that, it is extremely hard to address this kind of challenge and turn the Titanic around. That's where the science and technology really has to play. What are the game-changing technologies? And we don't know where those are right now. We have to try out a few. And what I'll present, I don't know whether they will actually change things, but there is a chance. And that's what we have to bank on, is to really go down deep into the science and turn things around. So which ones do we start? Well, here is a chart which is familiar to some of you, is what is the McKenzie curve of the carbon abatement. I'm not going to go into the details, but this looks at sort of the various things that one can do, and negative cost essentially says that it pays for itself and pays more. And think of this as the lowest hanging fruit. What it says also is that while there's all these options, economically, energy efficiency makes a lot of sense. Even if the numbers may not be quite correct, efficient use of energy is one of the applications that we would be looking for. Of course, we have to look at the supply side as well and decarbonize the supply in some way. So what I'm going to do is to talk about some initiatives that we work on. Bill has seen some of these before in LBL. And talk very briefly about these things and then go into something that I do. But when I discuss this, I'll also mention some of the things that I do scientifically in these initiatives. So one is, I'll talk about the Helios initiative, the buildings, storage, grid, and CO2 capture, etc. If you look, one of the programs that we have is the Helios program, which is conversion of sunlight to fuel. And it is broken into 4 paths. This is cellulosic path to a fuel. These are photosynthetic microbes, which the metabolic pathways can be turned around, can be manipulated in a way that it can use sunlight and produce hydrocarbons. And these are non-biological, artificial photosynthesis. If you can understand in detail how photosynthesis really works, which we don't understand, then perhaps we can replicate it in a way that is more efficient. Today it's 1%. And then the photovoltaics and electricity. I'm going to take this part and talk a little bit about some basic science that we are trying to do out here. And this is funded by Department of Energy and BP, and there are 3 centers associated with this. So, of course, if you do PV, these are 2 options that we have. One is the traditional way, and thereby you have to take silicon or polycrystalline, or single crystal, or amorphous silicon, and do it this way, or you do roll by roll. And if you have to do in a way that can be mass produced, we're talking about hundreds of miles of coverage, 100 mile by 100 mile coverage, to be able to match up with the demand of electricity. It seems likely that this may actually succeed. But if you have to do it with a plastic or polymer based, then you have all kinds of issues that come up. Because if you use polymer, the diffusion lengths that you have of excitons are typically 20 nanometers or so, 10 to 20 nanometers. So you have to nanostructure them. The other fundamental issue that remains unresolved, or I should say partly resolved, is what happens when you take an organic material, like a molecule, and bring it in contact with actually a conducting material, like a semiconductor or a metal. That interface in all these issues turns out to be the critical factor in how electrons transport or go from one medium to the other. And that is something that under this Helios project, under this particular thing that we're looking at, is that when you have a molecule in contact with a metal, and hopefully we can get molecules which are rectifying, or junctions which are rectifying, so they can separate out charge. But when you bring a molecule in contact with a metal, how do the molecular orbitals line up in a way that you can tune it, in a way that you can transition the electrons with low resistance, with low barriers? That is not something that is fully understood. And that is something that we are probing using probes like scanning tunneling microscopy. This has been done before, where you measure the transport of charge through these things and using current voltage characteristics, trying to understand what the band structure is like. But that alone cannot address the whole issue of electronic structure. So one of the new techniques that we developed is to apply, in addition to a voltage, use the same instrument to apply a temperature difference. And what temperature difference tells you is that you can actually you can look at what kind of a junction. Is it a P junction or an N junction? Because the sign of that voltage that you get, the thermoelectric effect, gives you insight about the charge transport. Again, in the interest of time, I won't go into the details, except for the fact that we can actually measure the thermal power of single junctions, or single molecules of these junctions, and more importantly, identify the location of the Fermi level, which is the chemical potential with respect to the molecular orbitals, the highest occupied orbital and the lowest unoccupied orbital, which turns out to be an important factor in how this transport happens and what kind of resistance you would get out of these molecular junctions. So we are now looking at these. These are benzene dithiols, dibenzene dithiols, tribenzene dithiols. We are now looking at different kinds of molecular groups that were attached to the metals. Like you can change to amines, you can change to cyanides, and they have various different effects of how they position themselves. And if you take a molecule, you can change the functional groups. You can replace a hydrogen in a benzene with fluorine or a chlorine, which withdraw electrons, or you can change with a methyl group, which throw electrons in, and see how this electronic structure actually changes. So that is something that we are pursuing, and we're getting some insights of how to design molecular junctions so as to rectify and thereby separate charge by simply assembling molecules with metals. So that is what is going on, which hopefully might lead to some interesting photovoltaic devices. Let me say a little bit about this on the thermal side. If you look at solar thermal in the past, this is still the cheapest way of producing electricity from solar, is solar thermal. And there are 2 ways of doing it. One is concentrating, going to high temperatures, and then using a Carnot or using an engine, like a gas turbine or a steam turbine, and thereby producing power. Or you take the low temperature version, which is there on roofs, etc., and you heat it. The biggest problem out here is that you got to produce electricity or use it directly, it's very hard to store it. There is thermal storage, but thermal storage has its own limitations. So the reason this happens fundamentally is because when you absorb a photon, you get 2.5 electron volts, you get electronic excitation, and immediately within picoseconds, you get phonon generation because you get all these decays, phonon effects, and you get multiple phonons generated. And the whole thing happens in about a picosecond. So as far as the system is concerned, it is essentially instantaneous. And you can't really change it. And the whole system design of using thermal storage and all this is based on that. So we are saying that, okay, this in fact is scalable right now. But there's a whole cost associated with putting these mirrors out there, turning the mirrors, when you have, the sun moving around, and then you have to go to high temperatures, and then you have to use molten salts, etc., for storage. Why can't we store this in a different way? So this is what we are now engaging in, is that if you now take something which you excite using the photon and put a kinetic barrier, then you could then trap this in a metastable state so that it does not come back. And then if you could release it catalytically, reduce the barrier, and then release the phonons on demand, it changes the whole system diagram completely. And this is a collaboration with Peter Vollard in chemistry, Rachel Siegel in chemical engineering, and myself, where you're looking at a molecule right now, which is in this case an organometallic ruthenium complex, which when you absorb sunlight, it twists into this metastable state at a high energy state and stays there for years. And then when you expose it to a catalyst, it turns around and releases the heat. And this is actually working. The problem is that this is now ruthenium, which is not the cheapest of materials, not the most abundant of materials. It works for osmium, which is in the same periodic, in the same group in the periodic table. Osmium is not the most readily available material. But it so happens, if you look at the periodic table, right above ruthenium osmium is iron. And that is what we are now going for, is that how do you design the ligands that hang out here and put iron out here and make it work with iron? And there's all kinds of density functional theory calculations that are going as to what kind of structure would you get to be able to do this, and then make sure that the absorption spectrum falls somewhat in the visible part. Otherwise, you can always do this in UV. But the visible part is what is critical. And that is something that we are looking at now. And there's a whole sort of research group that is looking at this particular one. But what it does is that it separates out the collection, storage, and heat generation. And I'll very briefly flash this thing. This is what it could then look like. You could have a pond of photoisomer molecules that you can collect somewhere in Nevada. Okay? And then you could transport it if you want. But what you need then is a heat exchanger, a catalytic heat exchanger that generates the power, and you could use for high temperature, you could use the same heat exchanger for low temperature, depending on your mass flow rate and heat exchanger design and how you use it. And it completely changes, separates out the collection to this thing, and then otherwise you don't have to co-locate your power generation with your, and the use with your collection, which nowadays what happens in Nevada and Arizona, etc. So this is something that we're looking at, which potentially could fundamentally change things, but of course there's a long way to go. I'm going to talk a little bit about buildings, because buildings is an area which we have been looking at quite actively. It's not an area that has received a lot of attention, but if you don't solve this problem, we're in trouble. Let me explain why. Here is the energy use in the United States. The largest sector for energy use is in buildings. About half and half are residential and commercial. And residential, there are about 60 million homes, and there are about 5 million commercial buildings. So if you really want to address the lowest of the low-hanging fruit, we are going after this. But of course, there's an issue out here. This is where the energy is used in a building. About 50 to 60% is heating and cooling. In commercial buildings, about 26% lighting. 72% of the United States electricity goes into building, and 55% natural gas. And there's a huge issue about what percent of GDP, how many people it employs, and the utility bills. So it is unlikely that we'll address climate change and energy security problems if we don't address buildings. And of course, we have to address transportation, etc. So what is the scientific issue in buildings? Well, let me explain. The goal that we're trying to create a bold initiative of trying to get to what is called zero net energy buildings. Essentially what that means is 80% reduction in energy consumption of new buildings and at least 50% in existing buildings. And these are very aggressive numbers. And this can be done today, but they're very expensive. The question is, how do we do that in a cost-effective way? And this involves people from architecture, from engineering, from public policy, from various divisions in LBL, computational research, all coming together and creating this initiative. If we do this in 80% reduction, that means 5 times more efficient than today's buildings, in new buildings, and at least twice in existing buildings, and while enhancing health and comfort, not turning off the lights, the impact it could have is substantial. This is the projection of the energy consumption in quads of commercial buildings, and this is the amount that it would save. This is about 4.5 quads out here. 4.5 quads is about half the electricity, more than half the electricity that is produced by all coal-fired power plants today in the United States. So essentially, if this were to happen today, this is 2030, if this were to happen today, you could shut down half the coal-fired power plants. That's the impact. And if this load can be provided by renewables, hydroelectric, nuclear, then of course you have an impedance match out there. And then you could say that buildings, commercial buildings, are essentially carbon-free or carbon neutral. Of course, this is assuming the growth rate the growth rate for buildings is about 1.7% per year in the United States. It's 7.5%, 7% in China, 8.5% in India. That's where the new buildings, that's where the big opportunities are. And we're getting phone calls from China and the Infosys and other IT companies saying that we want to reduce energy consumption in buildings because we get power cuts and the supply cannot keep up. And this is a huge opportunity to look at technologies that could reduce the energy consumption. So where is the science and engineering behind it? Well, here's the opportunity. People want to get to zero net energy building. Here's a reality check of LEED buildings. LEED buildings are leadership in energy and environmental design. These are supposedly the best, most green buildings that are around. Here's the reality check of what actually happens. This is the spread in the buildings. This is what it's designed for. This is the actual in gold buildings, gold and platinum. This is silver. This is certified buildings. You have the energy consumption per unit area all over the place. And if you look at the actual to design ratio, you have factors of 2 different from what you actually designed for. Okay? And one of the reasons is a policy issue. The most aggressive policy is in California called Title 24, where it is the performance of LEED buildings is based on design performance. No one ever measures them. Only 5% of the buildings are actually measured. This is, I mean, when I looked at this is the only industry I know, the big industry I know, where a product is made and delivered without ever testing. And this is just shocking. So not only does that policy have to change, and we might see some national standards for buildings where you have to meet. Standards is always the bottom line. There needs to be some things that pull the market as well, which has financial incentives, etc. But that's a policy issue. I won't go into that right now. I could if there are some questions. But here is the engineering issue out here. When we look at buildings, we have to think of them as a system. And you have HVAC, heating, ventilation, air conditioning, windows and lighting, all have influence on energy. Appliances, materials, if you can put storage in building materials, there's heat conduction, on-site power and heat, appliances, natural ventilation, indoor environment. In San Francisco, there's really no need, for example, to use a heating or for that matter, air conditioning if you use natural ventilation, but people still use that, and storage. If you look at it as a system, there's no question we have to improve the efficiency of HVAC, and the carriers and the trains and all are doing that. But that's not enough. We know that you can let's take an example of a car. You can have a very efficient engine, you can have a very efficient brake, but if you drive with your brakes on, you very efficiently waste energy. And that is what is going on in many of these buildings. It's fighting itself. So what we need to do is to have them cooperate. And what we need to do is to create something called, what we are calling, a building operating system. And that has never been developed. So let me just walk you through, allow me to walk you through. Let's say you have a building. And you have a dynamic information, which is occupancy, temperature, humidity, air quality, light, etc. And you have static information, architecture, floor plan, etc. you want to get to know where things are happening and what are things. So maybe you have some sensors, and you have a network communication. And then you have some static information which goes into a design. This is already built in to something. And around that, you create a building operating platform, a building operating system. And what would it do? It will make decisions, hopefully smart decisions. As to which ones, for example, you have heating and cooling, you have many options. You could have a centralized air conditioning or heat pumping. You could have waste heat for somewhere. You could have thermal storage, external ventilation, or you could have local controls in rooms. And which ones to turn on is something that should minimize the energy consumption and yet maintain the comfort. Okay, so this is a system integration issue. Well, you have plug loads, appliances. There are lots of plug loads that are always on, that need not be on, that should be turned off if you can. There is lighting. For example, you could have windows, you could have facades and shades. You have electrical lighting. And electrical light, they all have influence on the temperature, which on heat load, which will influence the HVAC. So they're all connected. And then you have the interaction with the grid. You have utilities, and where you can have storage, and you have on-site power generation, and you may get information of electricity tariffs and carbon emission rates, etc. And you have current and future weather. At least for the next few days, you know what the weather, what the weather is like. And if you have on-site power, you can get the waste heat from here and use it over there. That's the coordination that does not happen. In fact, only elements of that happen today. And of course, now you want to optimize and visualize the energy consumption and get to minimize the energy consumption or minimize the cost, depending on what the carbon rates are, etc. This sort of coordination and cooperation of a building operator, the brain behind a building, does not exist. What we have today are building operators who are, some of them are very smart. They're trying to do this, but you're looking at a 1,000-room building. And for someone to be able to zone and do all that is a humongous task. It's asking too much. You don't have, you have automatic pilots in a plane for good reason. So that is something which I believe is an engineering challenge of the nature that perhaps the IT people faced in operating systems, etc. So this is something that we are building right now, developing, and that's going on in this area. And there's a similar initiative on the residential side as well. Let me briefly talk about transportation. So obviously in transportation, the engines will remain for a while. I think it's fair to say, whether it's transportation or power generation. And there are a lot of issues. Princeton has been the hub of combustion research for a long time. And I'm preaching to the choir out here, what is required. But some of the things that are basic science and engineering challenge, how to take things at the molecular scale and affect design over here and vice versa, is something which has remained a challenge. And I won't spend too much time out here because the experts are really here. But I also say that there are some opportunities in terms of looking at sensors and materials that can withstand high temperature and high pressure, that can be inserted inside and wirelessly connected, and so that they can be used to control the combustion rates, etc., and the power generation, and reduce the environmental impact of combustion. I'll just leave it at that, and we can talk about it during Q&A. But one of the things that I think is a game changer is storage. Given the fact that the biggest growth in transportation is likely to be in the developing countries like China and India, and they have coal reserves and they do not have petroleum reserves, if there is an opportunity to provide the storage capacity, and batteries is one way to do that. Well, if you look at the history of battery, this is energy density in terms of watt hour. This is volumetric. This is gravimetric out here. The doubling of energy storage capacity in batteries has typically taken 60 years. And that's not a Moore's law that we are really proud of. So this is a time for game changing out here. And the question is how? Lithium ion, of course, there's a polymer lithium ion. Lithium metal can go to higher densities. And where we need to be is over here and higher. Let me sort of show you sort of.
Where is the gasoline fuel on that?
I believe the energy densities are way higher.
Yeah.
I don't think,
magnitude.
at least an order of magnitude, if not more.
Okay.
Yeah. This is, oh, there's IC engine. I think, I'm not sure this is actually correct. This is probably even higher energy density than this. But here's what is called a Rigoni plot. This is the specific energy, specific power, and plug-in hybrids over here. This is a hybrid vehicle, the Prius, etc. And this way electric vehicles have to be. So the capacity has to be increased by a factor of 2 or 3. One way to do that is to go to pure lithium metal anodes. But when you do that, you get things like when you do charging and discharging, you get all kinds of dendrites which form with short circuit. And we see that in our computer batteries, and we can throw away the battery. But in a car, that's very expensive. So one innovation that has come up, and this is my colleague's work, that the battery program comes under my division, so I get to see all this, is these are the dendrites that form. So you have to somehow block these dendrites. And his innovation, this is Nitash Balsara in chemical engineering, is to use a block copolymer as the electrolyte, which allows lithium ions to transport through a region out here, these holes out here, but blocks the rest of it is the soft part of it is PEO, polyethylene oxide, and the surrounding part is polystyrene, which is what helmets are made of. And the polystyrene blocks these dendrites because of the size. These are typically microns in size, but it allows the lithium ions to go through. So this certainly takes care of the energy density. But because you have a polyelectrolyte and reduce the transport of lithium ions, the power density goes down. So now there's a trade-off. The challenge remains, how do you increase the power density, that is, you have enough lithium transport per unit time, and still maintain the energy capacity of pure lithium anodes out here? And this is still a challenge. But this has been, of course, spun out into a startup company. They're making a lot of progress out here. But the good thing that has happened is that they have testing done on several charging and discharging, and they have been able to maintain the integrity of this batteries. But in addition to that, this is just transportation. Storage in general is probably the biggest game changer when we come to the grid. We're talking about gigawatt hour level storage. And that, if you look at this next generation smart grid, there's a lot of information technology that is being used. But you have to the grid has to instantaneously impedance match the supply and demand. If you could put storage out there, it is a game changer because it takes away the different fluctuations in the renewable. It enables the renewables energy, and that it still remains a big, big challenge. A lot of us are thinking about it, but there is no solution at this point. So here is sort of grid level storage. Here's the discharge time in seconds, and here is the system power in megawatts out here. So here's a gigawatt. And pumped hydro looks good, but where hydro is available is not often where the renewable energy is available. So that is a mismatch. The batteries out here, so while the transportation lithium-ion batteries, energy densities are very important. But when you look at grid level, it doesn't need to be mobile. You could go to stationary batteries where the metrics are very different. And if you can then stretch this in a cost-effective way, then perhaps we could do that. Again, coming back to storage being a very, very critical area that we should be looking at it scientifically to see how we can address this challenge. Let me very briefly talk about CO2 capture and sequestration. This is obviously a huge challenge today. If you could do that, it could enable sort of the coal-fired power plants. I don't know if you've heard the hearings for the Secretary of Energy. All the senators from coal states were asking, what about clean coal? And it sort of almost always comes down to, can you capture CO2? The way it is done today, and this, if you break down the problem, the capture part of it, the separation of CO2 from the mixture, you have to, of course, work against entropy, and you have to provide energy. That remains the most expensive part of the CO2 capture and sequestration. Of course, the sequestration part, how you do it, has major environmental impacts if there are accidents, etc. But the capture part today is very expensive. And 1/3, almost 30 to 33% of energy of a coal-fired power plant goes into the capture part, and that makes it cost ineffective. So the question is, how do you reduce the cost? How do you make the thing more efficient in terms of capturing CO2? It turns out to be a separation problem. Whether you separate CO2 from nitrogen or oxygen from air, regardless, the air separation turns out to be a big challenge. And so what we need is, what is done today is CO2 is dissolved in an amine solvent. Okay, so it's basic in nature, and CO2 is acidic, and there's some kind of a weak chemical bond. So you dissolve it as volumetric. So you pump CO2 in this amine solution, and it dissolves in there, and then you have to heat it to separate out the CO2. And that turns out to be, the heating part, energy inefficient. So we're looking at this and said, are there other ways of doing this? And I'll just very briefly talk about this. Whoops. Let me go back. So there are two possible ways. One is surface-based, which are membranes, metallo-organic frameworks, etc., which you can make materials with very high surface area, which can bind to CO2, and thereby you can capture CO2 and then separate them out, and then concentrate them and make it supercritical, etc. The other is the volumetric. Is it taking current amine-based or ammonia-based solvent-based approaches and make them more energy efficient? There are lots of things that you can take waste heat and use it somewhere else, or use a different approach, which I'll very briefly talk about, that we're starting to look at right now. So these are the options. Volumetric is good for scaling, because if you're talking about tons of CO2, if you have a volumetric process, that turns out to be, it scales in terms of cost. It actually, the bigger, the better in terms of per unit weight. So that's what I'm particularly interested in the supercritical. So what is this approach? This is untested right now. We are trying it. Is that if you take, let's say you take a mixture and you have this is a temperature entropy diagram, a typical thermodynamic, a vapor dome out here, liquid and superheated vapor. And you take a mixture and you increase the pressure. The partial pressures of both the components go up, and at some point, one component will become supercritical, the other will remain subcritical in a gaseous form. In a supercritical phase, you essentially form clusters. And the clusters have certain lifetimes, sometimes picosecond, nanosecond, etc., and they have certain size distribution. But essentially what you have is a separation, in some phase separation, if you have one medium, one phase, one species in a cluster form, and the other species in a purely gaseous form. Once you do that, you could then possibly take gravimetric approaches like centrifuges to separate out the mass-based ones, and thereby you can take the gaseous part in the clusters, and you could sort of repeat it in a cascading form, and thereby. So this is some approach that we're now just starting to do, but it has a chance of addressing this issue in a volumetric way as opposed to a surface way. And the question then is that, are there some seed molecules that I can put there which will increase the lifetime of these clusters? And possibly there will be. And so that is something that we are just starting to explore. And there are some computation going on with Baron Schmidt. And we're now starting to build a system to see what's the lifetime, what are the size distribution of these clusters. And we're also looking at the literature to do that. Let me now stop and sort of look at this particular aspect of waste heat. And that's where I've spent some time in researching the waste heat out here, which is half the primary energy. And it seems like a big waste to sort of ignore. If you could convert sort of 10% of this, 5 quads, that is almost half the electrical capacity of the United States. And if you put a value of that, I don't know what the price of electricity is in New Jersey. In California, it's at least 10 cents a kilowatt hour. I'm assuming at Texas level, 5 cents a kilowatt hour. And with 5 quads per year, it's about $70 billion per year. This is just being wasted if you could just convert it. How do we do that? There are potentially many different ways. We are trying out one way. And the way we are looking at it is using semiconductors, using thermal electricity. And this is when I'll sort of dig in and go a little bit deeper. We have, this is called a Seebeck effect. If you have two materials forming junction, if you have a temperature difference, you get a voltage. And this could be used in the form of electrically putting P and N junction in series, thermally in parallel. This works as an engine. You take waste heat, and you can generate electricity. You can generate a voltage and current, and thereby you can run it across a load, and that's an engine. Or you can take the same device and apply power to it and grab heat from the cold source and dump heat to the hot source, and you can use it as a refrigerator or heat pump. So it's a heat engine. and follows Carnot's, all Carnot's law. You can get this off the shelf today. But the problem is that the material, the semiconductor that is used, is bismuth telluride. And of course, it's a very exotic semiconductor, and for good reason. But that is expensive, and there is low efficiency. And the efficiency follows a figure of merit called ZT. And ZT is a combination of properties. It is the Seebeck coefficient squared, electrical conductivity, and this is absolute temperature, and this is thermal conductivity. And the efficiency of these devices, which is the percent of Carnot, increases monotonically with ZT. So you want to maximize ZT. That means you want to increase the numerator, which is electronic, and you want to decrease the denominator, which is the thermal conductivity. And while each of them can be changed by orders of magnitude, the value of ZT has not changed much. And I'll give you the reasons why. So right now, bismuth telluride is ZT of approximately 1. You get about 20% of Carnot. Where you really want to be is about 30 or more. The reason we want to use this, as opposed to the question is, why can't we just use gas turbines? The problem is that the temperature differences in waste heat are so low. They're low-grade heat. Although there's a lot of energy going, temperature differences could be 100 degrees, maybe 150 degrees. It's very hard to run a gas turbine. You could possibly run an organic Rankine cycle, but we are trying to see whether there could be cheaper ways of doing it. So here is, how do we get to ZT of 2 or more is a challenge. And the history out is the following. ZT, the bismuth telluride and its alloys, were discovered in 1955. And it was 0.6 or so. It became 0.7 or 0.8. And a lot of people at that time thought you can extrapolate it. And then by 1990s, you can get all solid-state engines, refrigerators. Obviously, that didn't happen because ZT did not increase for a long time. Only recently we have seen some increases. So why does it not increase? Why is it so difficult when each property in ZT can be changed by orders of magnitude? ZT itself cannot be changed even by 20%. And the reason is the following. That if you take a semiconductor and you start doping them to increase the carrier concentration, sigma goes up, the electrical conductivity. But S goes down. And there's an optimal in S squared sigma, which happens to be degenerate semiconductor. And the thermal conductivity, so they're correlated. The thermal conductivity, as you increase the carrier concentration, you have the baseline lattice contribution, which is the vibrations of the material. And then you have an electronic component. So as you increase, you get the electronic component. So they're all correlated. And you get this interdependence of properties. You change one, the other changes. I call this the Bermuda Triangle of thermoelectricity. A lot of people have spent their careers trying to change this and have not come out of it. And we are in it right now, trying to get out, but can't. One of the things that you have to do is to reduce the baseline lattice thermal conductivity. That's why you go down the periodic table in your semiconductors and take heavy elements, because heavy elements will vibrate at lower frequencies and thereby transport heat at a much lower rate. And so that's why you go down to bismuth telluride. But of course, that's not the abundant semiconductor. So people said, okay, how do we change this? The reason we have this dilemma of this, at least the electronic part, you have to go down to the band structure and ask, what is the thermal power? And if you look at it, you have to say that, okay, if your Fermi level, for example, the chemical potential is deep inside the conduction band, which is a metal, then you have this distribution of electrons. And if you take a piece of metal and apply a voltage, you get a current. And ask which electrons contribute to your electrical conductivity or conductance. And you'll find that the electronic distribution is close to the Fermi level. This distribution out here, these things are all occupied, and you can't really transport because they're all occupied out here. You can't energize them. Here is where the electrons really contribute, and you get a net current out of these. This distribution, it turns out, is not quite symmetric with the chemical potential. There's some asymmetry out there. And that asymmetry is the origin of the thermal power. If it is perfectly symmetric, there would be zero thermal power. So you want to create asymmetries. So the reason now you have this dilemma is because if you put your Fermi level deep inside the conduction band, your asymmetry goes down, but you get a lot of carriers. So electrical conductivity of metals is high, the thermal power is low. If you now take a semiconductor or degenerate semiconductor, put your Fermi level close to the conduction band edge out here, you get a lot of asymmetry, but you don't have enough carriers. And that's the dilemma that people essentially realize, that it's very hard to change this, except if you do a few things. If you now make heterostructures, you got metal semiconductor heterostructures now, and if the band edges, the offsets, are on the order of kT, you might be able to skim off and create asymmetries. This is like evaporation of water or evaporation of liquids. You create a barrier and you evaporate some, the hot one, and you cool down the solution. That's essentially this phenomenon out here, often called thermionic emission in semiconductors. Or you create quantum structures. And if you create 1D, 0D, quantum confine the electrons, you can create asymmetries of all different shapes and forms. And if you pin your Fermi level somewhere in this asymmetry, voila, you get a lot of thermal power. And this is what motivated people to go to nanostructures. What people found, so the people made nanostructures. This was Millie Dresselhaus at MIT, who predicted all these things. So people went into nanostructures, and they made superlattices, they made quantum dots, and they found quantum dots serendipitously, and the ZT did go up. But what they found was that not only did the numerator, which is what they were trying to push for, numerator did not go up. In some cases, it went down. But the thermal conductivity went down even more. So it was for different reasons that ZT went up. So then the dilemma happened. We said, okay, why? The nature is telling us the conduction is where perhaps the opportunity is. How do we reduce the conduction? And so one has to ask the question, how is heat conducted? So I'll give you one sort of slide primer of how heat is conducted in a solid. You have atoms, you have springs, which are chemical bonds, and you jiggle the atom out here, and you create waves, just like you would have in a spring mass system. And these are acoustic waves of very high frequency, hundreds of gigahertz or terahertz, which carry the heat. And just like any waves, they scatter of boundaries, they scatter of particles or defects. And the spring, the chemical bond is a little nonlinear, so they can interact with each other and actually mix, and that's called phonon-phonon scattering. These are quantum of vibrational energy is called a phonon, just like quantum of electromagnetic energy is called a photon. So the statistics of phonons is exactly the same, almost exactly the same as blackbody Planck distribution. So it follows a blackbody-like distribution, and you have the peak of the spectrum going to higher and higher frequencies or shorter and shorter wavelength as you increase the temperature, what is called Wien's displacement law. So the analogy with radiation is certainly there, except for one big difference. The speed of light is about 4 or 5 orders of magnitude higher than the speed of sound, because that's what transports this energy. Thereby, the lambda max of the Wien's displacement law for photon radiation, for the sunlight, which is, you have the peak at 500 nanometers, which is the green light. In this case, you can go down 3 or 4 orders of magnitude, and lambda max, the peak is at, the energy that we are using right now to exchange heat is at 10 microns. That's what happens. And for sunlight, is a half a micron. And for this, happens to be on the order of a few nanometers. So you have to get down to the nanometer level to be able to manipulate heat. So we said, okay, how can we reduce the heat? And one way to do that is to make alloys. And why you make it? So you take silicon and germanium and mix them, and you create scattering sites, like particles in the atmosphere, and thereby scatter the phonons. And you get to what is called the alloy limit, and people mistakenly thought this was a limit. You can't go lower. So we came up, and what people missed out was the fact that this is a very broadband blackbody radiation coming at you. And you're scattering them, but you're scattering them with atomic scale defects. What we hypothesized was the following, that certainly the alloys, which are atomic scale defects, will scatter these waves, the acoustic waves, but it'll scatter the shorter wavelength much more efficiently than the longer wavelength, just like the molecules in the atmosphere scatters blue light more than the red light and the green light. And that follows Rayleigh's law. So he said, if you want to scatter these medium wavelength phonons, you have to put nanostructures of the right size so that it scatters. So you want a wider distribution, which is analogous to putting clouds in the sky and scattering the green and the red and everything else. So this was the hypothesis. And then our collaborators at Santa Barbara, Art Gossard and his colleagues out there, created this semiconductor, erbium arsenide epitaxially embedded in a indium gallium arsenide matrix. And the question is the thermal conductivity of this composite lower than that of indium gallium arsenide, the alloy, the matrix itself? And certainly that is indeed true, that this is indium gallium arsenide thermal conductivity, and going down, this is indium gallium arsenide with these nanoparticles embedded. And so the thermal conductivity goes down by a factor of 2 or so. The power factor numerator in ZT, in fact, doesn't change. It increases a little bit. The ZT goes up by a factor of 2. And that was, we thought, was a rational design for a thermoelectric material. And now this is showing ZTs of about 1.5 or 1.8 at high temperatures. And this becomes possibly a power generating scheme. When we looked at this, we said, OK, this gallium arsenide and 3,5 materials are wonderful. The question is, how do we scale up? And scaling up 3,5 materials is not easy, especially when you're looking at power, where you need a lot of material. So we looked at this and said that, what are the most abundant materials on the Earth? And the abundant materials, in terms of semiconductors, is certainly silicon. And there are, of course, others out here, iron oxide, perhaps. So these are semiconductor insulators. But let's take the most abundant semiconductor, silicon, and see whether it would work. And that was a crazy idea. Because silicon, if you have worked on it, let me flip back. Silicon has a very high thermal conductivity. It is the spring in the chemical bonds is very harmonic, so the phonons travel a long distance, and they cannot scatter. And so thermal conductivity of silicon is about 140 watts per meter Kelvin. And the ZT of bulk single crystal silicon is 0.01. So everyone ignored silicon. Except for the fact that, and we realized it after a while, that the mean free path of these the phonons in silicon is very large, 400 nanometers. The electron mean free path is very short. So we decided, let's nanostructure silicon and see what happens. And so this is a collaboration with Peidong Yang in our chemistry department, where he came up with a process of taking silicon wafer, dipping them in a solution of etchants, and you get, voila, you get these nanowire forest. And the nanowires are a little bit rough out here. And what we find amazingly, and we're still trying to figure out why, is that the thermal conductivity of these crystalline wires, this is single crystal wafer, and inside it's crystalline, except the surface is disordered. It turns out to be, in this crystalline wire, approaching the amorphous limit. That is the glass limit. So we are creating a phonon glass out of a crystalline material, and electronically it's working as a crystal. This is sort of the holy grail. Electronically, the electrons are transporting through this, but phonon-wise, they're scattering, and they're behaving like a glass. And the ZT is actually about 1, in fact, higher than 1. It's behaving like bismuth telluride. So we are now trying to figure out what the heck is going on with the phonons out here. One hypothesis, and we don't know whether it's correct, we're testing it right now, is the following. That in an amorphous limit, this is the lowest limit that people have been able to go to, at room temperature about 1 watt per meter Kelvin, but 140 times lower than bulk silicon. It's very hard to see where this is completely disordered, and the phonons really cannot go very much more than the lattice spacing. So why is a crystalline material behaving like this? One option is something which I think Princeton is very familiar with, is localization. This is similar to Anderson localization, where you have, in Anderson, you have electrons going in a disordered medium, and thereby locally interfering in such a way that you have destructive interference. Here, people have shown this for electrons, for the metal insulated transitions. People have shown this for photons. What people have not been able to show, a lot of people have been trying to show this for decades now, to show it for phonons. Because it's a broadband, and because you have all these kinds of phonon-phonon interactions, you can have leakage. No one has been really able to show phonon localization. And what we think this disorder might be creating is these kind of local, there's multiple paths of phonons traveling, and then the phase canceling each other out, and then thereby scattering and localizing phonons. We are testing this hypothesis. We don't know whether it's correct or not. We'll see in a few months whether the experiments really bear out. Maybe it is not, but we're still trying to figure out. So let me just, I'll stop my scientific part out here, and with the very little time left, I'll just end with this global perspective again. So by the way, we are also looking at my colleague out here, Ashok Gadgil, who's has created this Darfur stove, very energy efficient stove for the people in Darfur, and so that they don't have to go out the women don't have to go out too many times to collect wood and get affected that way. And a stove like this has about a 3 kilowatt heat just wasted. I've been trying to see if you can take these and generate electricity so that people, they're off the grid anyway if they can have gridless power. So that's something that we're also trying out, and there's some students involved in this. Let me just end by saying that, of course, we are in a historic time, but I just want to reflect on another time in history where this transition that we are seeing indeed happened. It seems like, I was not there, but it seems like it happened, and to see what kind of innovation really changed things. So at the end of the last century, there was a lot of debate about what was the most important invention of the 20th century. And of course, these are debatable topics. There's no set conclusion, but I like the analysis that journals like Nature and all did. So one would think, and if you take a poll out here, you would get things like aeroplanes, nuclear, space flight, computers, etc. And the answer came out of this analysis was no. And that intrigued me even more, because I would have guessed all these. I would not know which one to pick. So the analysis, here's some history. In 1898, there was a calling upon science to save the world from impending starvation. And this is sort of William Crookes. And this sort of analogous to the formation of IPCC, if you may, of calling upon science. And why? Because there was growing population, lack of nitrogen in the soil in Europe, and bacteria and biocatalysts were insufficient to grow food. In 1908, Fritz Haber discovered a catalyst that would combine atmospheric nitrogen with hydrogen to form ammonia. And the catalyst happened to be uranium at that time. Of course, the new catalysts were found. In 1913, Carl Bosch developed processes to mass produce ammonia, and that led to fertilizers, and the world population grew from 1.6 billion to 6 billion people. And that, one could argue whether that's a good thing or not, but nevertheless, in terms of affecting humanity, I don't think any other of these inventions touched as many human beings as this particular one. And of course, they received their Nobel Prizes, etc. But I think we are at that moment in history, I feel, that what we do in energy and environment could have, this is at least once in my lifetime, that we could do that could potentially touch the humanity in that way. And let me just leave you with some visuals. This is the population density of the world. And we are over here. I come from here. And here is, this is where I originate from. And you can see the high population densities out here in China, etc., and there's some Europe, and largely sparse. Now let me put up on this, now let me show you the lighting, which is where the energy is used. Of course, very bright out here. This is Wasilla, Texas, I think, which is now forgotten, long forgotten, I suppose. But we get reminded once in a while. And this is Europe. This is India, China, Japan, and African nations out here, and Australia and the coastline. What is striking is when you superimpose those two, and it sort of brings out some of the problems, is when you superimpose them, you find these bright spots out here with not much population, and you get this high density of population with not too many lights. And that mismatch that's really the challenge. How do we somehow reduce energy consumption, matching the population? The question that we're all asking, and look at this population out here where there are no lights. If they start turning on the lights the way we have done, the West has done, we are in deep trouble. And this is a global issue, and I hope Princeton and other institutions look at this globally. At least that's how we are trying to do, look at this globally and see what technologies would pass the test of China, India, other developing countries, while also addressing technologies in the United States. So let me stop here and leave you. I've taken too much of your time. I appreciate that very much. Thank you very much.
questions?
Sure, sure.
Have time for a few questions.
In your discussion, you talked about capturing the waste heat from the bottoming cycle. But you didn't talk about the topping cycle, and that's been an issue in some past. Is your impression that that's not as ripe an area for research? Or what is your
No, I mean, I have the charts I didn't show. The average efficiency of United States power generation is about 35%. The average efficiency of Japan is 40%. And there's room at the top. I didn't cover all the things. There's room at the top to increase the efficiency by, for example, going to high temperatures with high temperature materials, et cetera, in gas turbines and designing them the right way to increase the efficiency. There are two ways of increasing efficiency is to grab the heat from the bottom or increase the temperature on the top. So absolutely.
Because the bottom, presumably by distributing the power sources, you could use that bottom heat to heat houses. You can't use the top to do that because that's very high temperature. So there may be an option.
Oh, absolutely. I think the combined heat and power is being used, as you said, taking the waste heat, but it's not being used as widely. I mean, you'll be surprised to know how much heat is wasted in these. After we published our paper, we got phone calls from glass manufacturing guys in Texas and other places that we have 6 megawatts of heat just going at 450 degrees Celsius. And I told them, you don't have to come to me. You can just take a absorption chiller and do air conditioning with that. And they just haven't paid attention to it because energy is cheap. And I think there's a lot of opportunity out there.
But a lot of legislation prevents that. I mean, the paper industry was something where you can use the waste heat from generating electricity to do much of the drying the paper industry needs. But in a sense, that was formally forbidden because the utility is a different animal than a factory.
Right.
Law prevents that from happening.
So in many of the, so this is now sort of turning to policy. I mean, in California, there's something called decoupling that has happened where the utilities are incentivized to reduce the energy consumption of the user because they can take the difference and charge it to the ratepayer. That's where the electricity prices are higher. That decoupling, that's called decoupling because from your revenue from the actual sales of electricity. The decoupling has happened in about 10 or 11 other states. It hasn't happened countrywide, and there's no reason why it can, because it works wonderfully, the utilities in California. So, yeah.
You mentioned the original catalyst for the ammonia synthesis was uranium. But of course, it turned out that the best catalyst shortly after turned out to be iron.
Right. Right.
Just plain on rusty iron. That's all there is to it. So it goes with the idea of using the most abundant element.
A most abundant element, yeah. Uranium may not have been scalable, and could have, yeah.
One of the huge sort of scientific areas that's advancing at an enormous rate now is biology, broadly biology.
Right.
Do you see a big interaction here? I mean, do you see a lot of biological inspiration in energy generation, transfer, and so forth, or is it sort of scientific curiosity? I mean, I know you've also worked in nanoscale bioengineering.
Yeah, I mean, I'll talk from a little bit of ignorance out here because I haven't gone to the details of the metabolic pathways, et cetera. But biofuels, from what I'm reading now, they were looked at even in the 70s. But the big difference is that the biology that we know today and the tools that we have are quite different. In fact, much more advanced than what we had in the 70s. That's one huge difference in the bio, and others may not be as different. But this particular one. So I think we are seeing a lot of people, at least from my own experience in Berkeley and other places, is that we're seeing a lot of that know-how that went into the medical field being diverted now or towards energy, and saying that how can we use the different cell cycling pathways or metabolic pathways to take what was E. coli. You probably all know Jay Kiesling work in artemisinin and how he has taken those precursors and are making jet fuel out of that. So that's the kind of thing which is fascinating. I mean, I don't know much about it, but that's a huge opportunity. The question again comes back to scale up. And whether it will make a dent in the petroleum consumption, which is what 150 billion gallons a year, what would it take to scale up to that level? And that, I think, will take some time, I think.
On your work on thermoelectricity, if you're able to make a silicon-based material work in that application, you have an idea of what level of ZT you have to get to be competitive?
Yes. Yeah, so we looked at that. For bismuth telluride, you had to have a system ZT of 2. That's sort of which means the ZT material has to be higher than that because there's system parasitic losses, et cetera. For silicon, it's a little bit less. In terms of dollars per watt, it comes down to that. You could get by with ZT of 1.8, 1.7 or so. You can get by. You can do system level stuff that can reduce. So that's what we are shooting for right now. And the mark that I have a student now. He wants to start a company, and I'm holding him back a little bit. But he has done these calculations that you can get $1 per watt for silicon, whereas bismuth telluride you would get like $3.50 per watt installation cost. So, yeah.
In your supercritical idea, what sort of persistent time of clusters are you looking for this even to be feasible?
I don't know the answer to that question. What we have what we looked at the literature and found whether they were in the picosecond range. That seems awfully small. If we can retain them for in a nanosecond or longer, there we may have a chance. But to be honest, we haven't done the calculations of what the residence time ought to be. Yeah.
Let's thank our speakers.
Thank you very much. Thanks a lot.